Hello everyone. In this video, I would like to introduce you to LaTeX. I want to tell you what it is, why you might want to use it. I'll give you a quick introduction to some of its features and set you up so that you can start writing your own documents immediately. LaTeX is a mathematical typesetting system. The history goes back to the 1970s when the computer scientist Donald Knuth created tech, pronounced with a hard C sound at the end. And then in the 1980s, Leslie Lamport created an easier to use version called LaTeX or LaTeX. And I should add that this is an open source project, so many volunteers have added to LaTeX over the years. LaTeX is a mathematical typesetting system that may sound mysterious to you, and it might be easier for me to say what it isn't. It is not a WYSIWYG program, or what you see is what you get, a program like Microsoft Word, for instance. Instead, in LaTeX, you start out with a text file, and almost as if it is a computer program, you compile it, and it produces your final document. One question you may ask is, this sounds like a lot of work. Why would I want to use LaTeX? Well, one reason is that it produces beautiful mathematics. It is very powerful in all of the things that it can create. But there are some other benefits for this system in which you start off with just a text file. For example, unlike Microsoft Word, where you are often using your mouse to pull down various menus and click off various options, with LaTeX, you don't have to lift your fingers off the keyboard. You can type everything, and although it has a steep learning curve, in the end, it is significantly faster to create a LaTeX document, especially one that has a lot of mathematics in it. Also, because the essential item in your LaTeX file is just a text file, it's going to be small, so it's easy to share. You don't have to rely on any proprietary software, such as something owned by Microsoft or Adobe. And you can create your own LaTeX documents on a Mac, on a PC, on Linux, on the web. It is very platform independent. And lastly, it is backward compatible. So if you created a document in the 1980s, you could recompile it today and get a fresh, clean PDF. Likewise, if you create a document right now, you can feel confident that you'll be able to compile it again in the future if you needed to. Another feature of LaTeX is that it encourages you to think about the content of your document and not on the layout. These are created in a way such that when you send it to a journal, the journal can input the text file into their template, compile it using their template, and create a document that looks like their journal pages. Or a book publisher could change some style files and generate something that would look professional on their end. So it is very publisher friendly. It is also the industry standard for many quantitative fields, such as mathematics, statistics, physics, computer science. So it is worth spending the time to get to know it. It also takes care of things such as numbering pages and chapters and sections and figures and theorems and tables and things like that. So you don't have to constantly tinker with numberings of such things. It has an indexing capability so that as you edit your book and things move around, the index keeps track of where the various items are. You can use it to generate bibliographies and so forth. So let's look at a typical LaTeX document. So on the screen, I have a very simple document. You can see it is broken down into what we might call the preamble and the body. So let's take a look at the preamble. For beginners, you will probably want to largely ignore the preamble. The first line talks about what type of document you're creating, whether it's an article or a report or a book, and so forth. So in this example, it's an article. The next line tells LaTeX what packages the author would like to add beyond the basic functionality. And so for the rest of this presentation, I'm going to assume that we have the GraphicX package that gives us some features in terms of adding figures to the document. And then the next three are packages created by the American Mathematical Society, the AMS Math package, the AMS Theorem package, and the AMS Symbol package. These all extend the capabilities for generating mathematical documents. Also in the preamble, you might include the author's name, the title of the article, the date that you want associated with your document, and many other things. You may want to do some formatting in this location, define new objects, etc. But for now, let's just keep it simple. In the next section, the body, it is bounded by a begin document and an end document line. In this case, the first thing we do is tell LaTeX to generate the title. So that will place the title and the author's name and the date and so forth in the final PDF. In this particular example, I have one section and I give the name of the section, which is preliminaries. And then after that, I have the body of the document, the text of the document. And so this is the basic outline. Also in this body section would be where you would include things like the bibliography and the index and so forth. If you are interested in just entering basic text, you type it just as you would ordinarily. Just type the words as you want them. There are a few quirks that I want to point out. One is that LaTeX ignores extra spaces, like spaces from your spacebar. So in this example, I put a lot of spaces between the word fathers and brought, but when this is compiled, you'll see that LaTeX just recognizes it as a single space. Also, somewhat oddly, it ignores carriage returns at the end of a line. So in this case, I pressed the return key after liberty, comma, and when I typeset it, it treated it all as one line. Of course, there are times when you really would like to move on to a new paragraph, and the way you do that in LaTeX is to put 2 or more returns. Or another way to say that is that if there is 1 or more blank lines between 2 paragraphs in the text document, that will generate a new paragraph in the compiled document. Sometimes you want to move your text onto a new line, but not create a new paragraph. And so to do that, you could put a double backslash. So I have 2 examples here, one where the double backslash is at the end of a line, and one where it's in the middle of a line. But in either case, when you compile it, it will send you to a new line, and you can see that it's not indented. That is telling you that it is not treated as a new paragraph. There are some special characters that are reserved by LaTeX for a special purpose. These are ones that you can't just type and assume that they are going to compile as is in the document. So these are the number symbol or the pound sign, the dollar sign, the percent symbol, the caret, the ampersand, the underscore, the curly braces, the tilde, and the backslash. So if you wanted one of these to appear in your final document, you have to type something special. In many of these cases, it's just putting a backslash before it, but some of them are treated a little differently. When you're writing, you may want to stylize your text in various ways, and it is not as simple as in Microsoft Word, where you highlight the text and tell the program to italicize it. Instead, you have to use your text commands to tell LaTeX to do what you want it to do. So in this example, I give the commands to do italics, to do boldface, and to underline text. There's another option which is called emphasis. And in this example, you can see that emphasis just italicizes the text. So you might wonder what the difference is between text IT and EMPH. Well, it turns out that using EMPH leaves it up to the publisher or the style guide to emphasize it in the way that they see fit. So oftentimes emphasis just means italics, but you could imagine a situation where a publisher would rather emphasize something by underlining it, or maybe to change it to a different color. And so in some ways, emphasis is a better option than just italics. Just like in Microsoft Word, you can create lists. So you can create itemized lists, such as this one here. Notice that to do this, we create an itemized environment. It starts with begin itemize and ends with end itemize. And for each item in the list, you put a \item, and LaTeX will generate the itemized list. You can also create enumerated lists. So this starts with begin enumerate and ends with end enumerate. And just as with the itemized list, you use the \item command to create a new item in the list. I also wanted to illustrate that for both itemized lists and enumerated lists, you can nest these. And so here's an example where we have an enumerated list inside of an enumerated list. Just like in many computer programs, you occasionally want to leave comments in your text file that won't appear in the typeset document. And in the case of LaTeX, you can do that by starting with a % symbol. So in this example, I have %, but this sentence will not appear. And then I have another situation where it's % and neither will this one. And when you typeset these, you'll see that those two sentences do not appear in the final document. One extremely useful feature of LaTeX is that it numbers everything for you, but you can also refer to these in a way that LaTeX will update it automatically for you. So to do that, you put \label, and then you create some unique marker to go in there. So in this example, I start off with the chapter, which is called integrals. And after we introduce the chapter title, I created the label chap:\integrals. That chap: does not have to be there. This just needs to be some unique marker, but I wrote it that way so that I would remember that I'm using this to mark this chapter. And then later in the document, you can use the \ref command to pull up the reference to the given chapter. So I have chapter \ref chap integrals, and when the document is typeset, that turns into chapter 5. And if I added or deleted a chapter in the book before chapter 5, then LaTeX would automatically renumber that for me, and it's not something I would have to chase around. Here's another example. In this theorem environment, I created a label for the theorem. And so then in the document, I could refer to that label. And in this case, that would produce theorem 5.7. And again, this will update automatically as I add or remove theorems. There's also an option for page ref. This will spit out the page number where that label appears. All right, let's talk about mathematics. There's two ways to put mathematics into your documents. The first is inline mathematics. So this will occur if you are writing a paragraph and in the middle of your paragraph you would like to insert some mathematics. So to do that, you use a single $, then whatever math expression you would like, and then ending with a single $. So $ on either end will generate inline mathematics. And so you can see in this example that the limit has the x going to 0 off to the side rather than underneath the limit symbol. And the sign of x over x is shrunken so that this whole object will fit nicely in line. So that's how the single $signs work for inline mathematics. But you might not be happy with how this looks. It maybe looks a little too small and a little too squeezed, and you'd like it to be full-sized. So to do that, you put \square brackets on either end of the mathematics. And when you do that, as in this example, the mathematics appears on its own line, centered and full-sized. So there are times when you might prefer this display style mathematics rather than inline mathematics. I should add that instead of the $ on either end, you could also use \parentheses for the inline mathematics. There are many, many different mathematical commands, and I can't go through all of them today, but I thought I would give you a brief introduction so you can see what kinds of things are available to you. So here's a simple one. I put in dollar signs, a squared plus b squared equals c squared. So I want you to notice a few things. So first of all, this is just a text document, so you can type it without lifting your fingers off the keyboard. To indicate that we want the exponent 2, we use the caret symbol. A few other things to point out here. First of all, it is convention in mathematics that variables are always italicized. So you can see that because A and B and C are inside these dollar signs, that when the mathematics is typeset, they become italiced variables. Numbers, on the other hand, mathematical numbers, should not be italicized. So the 2's, which are in the exponents, are not italicized. So you don't have to worry about that. LaTeX will take care of it, but it's important to recognize that that's the case. In this next example, I said A intersect B is a subset of the set 1, 2, 3, 4. And so to do this, the A and the B are just ordinary letters, as are the 1, 2, 3, and 4. To get the intersection symbol, I use \cap. So again, the \ symbol is going to be your friend. It will be used anytime you want to create some sort of special mathematical symbol. The subset symbol here is subset EQ. The EQ indicates that there's the equality line underneath the subset. Also, recall that the curly braces are reserved symbols in LaTeX. And so if you actually want curly braces to appear in your document, you need to put a \ before them. So notice that this is \ curly braces on either end of the set. In this example, I have the expression sine of x plus the natural log of x. And notice that I've used \sin and \ln. So these are recognized by LaTeX as predefined mathematical operators. Notice also that they are not in italics because these are functions and not variables. This example, I have it set up as a display equation. I did it as a display equation because I wanted to have the numerator and the denominator be full-sized values and not squeezed between two lines. We have the \frac command, which is generating the fraction, and then inside the curly braces are the numerator followed by the denominator. And notice here that the curly braces don't have \ before them. Curly braces in this context are used to tell LaTeX where the argument ends, the argument for the numerator and the argument for the denominator. So it sort of collects things up so that LaTeX knows what to do with them. My last example is this integral. So \int generates the integral. We have the _(-1) and the _1 to generate the lower and upper index for the integral symbol. Notice that I did put curly braces around the -1 because I needed to show LaTeX that that all goes in the lower limit. But I chose not to put it around the 1 because there's just one character there. And so LaTeX can put that in the upper limit. We have the \xqrt, which is the square root function. The curly braces tell LaTeX everything that goes underneath that symbol. And then we have the \frac for the fraction, \pi for the Greek letter pi. There are many situations that might come up, but I want to talk about a few of the ones that are very common. If I look at this typeset sentence on the right, as someone who reads a lot of mathematics, it'll pop out right away that that first x is not in italics, and it should be in italics. And if you look at the source code on the left, you'll see that the user had forgotten to put $signs around that first x, and so that is why it came out in Roman rather than in italics. So be sure to put $signs around your mathematics, even if it's just a single variable. Likewise, when you're writing a function, like a mathematical operator like sine, you want to put a \ before it. In this example, the first instance does not have the \, and when you see it typeset, all of the letters are in italics. So really the way LaTeX is viewing this is the variable s, the variable I, the variable n, and the variable x. But that's not really what we mean. And so you need to remember the \ before sine. Numbers should also have $signs around them. One way to see this is if you have -1, with and without the dollar signs, you'll see that they look different. The dash is different from the negative sign, the size of it and the spacing and so forth. So you need to put dollar signs around that. If you have a number that's just, let's say, a positive integer, you might think you can omit the dollar signs around it, and probably most of the time that would be fine. However, if we were to ask LaTeX to italicize this sentence, then what you'll see is that text numbers are italicized, whereas mathematical numbers are not italicized. So in this case, 1732 is a date. We would want that italicized, so we don't put dollar signs around it, whereas that gigantic composite number of Eulers is a mathematical value, and so we would want dollar signs around it. One other question that you might ask yourself is, what do I do with punctuation? Do I put periods and commas inside the dollar signs or not? So it turns out that often it doesn't matter. In this case, it'll look the same either way, whether it's inside or outside. However, if you do have a display equation like this, and you put it inside, the period will appear where you would like it, right after the 3. If it's on the outside, then it will center x minus 3, and the period will appear by itself on the next line, and so you don't want that. So at least in this case, you would want the punctuation on the inside. One thing that throws beginners is how to create dashes of various sizes. So you know from writing that there are hyphens and n dashes and m dashes, each of which are different lengths. And so in LaTeX, you would use 1 or 2 or 3 dashes in the code to generate the dashes of various lengths. One quirk that always throws beginners is how to create quotation marks and how to create single quotation marks. So we're used to, on our keyboards, just using the quotation mark and using the single quote mark. The problem is LaTeX needs to know whether you are talking about a left quotation mark or a right quotation mark. And so what you need to do is, for your left quotation mark, you need to press the back quote twice, otherwise known as the grave accent, twice. And for the right quotation mark, you want to press the single apostrophe 2 times. Likewise, for the single quotation marks, you want to press the back quote once on the left, and you want to use the apostrophe on the right. And that will generate quotation marks that behave the way you're expecting them to behave. If you write a lot of math, you are going to want to create matrices and tables and other things where you've created a grid of mathematical objects or a grid of text objects, something like that. There's far more to talk about than we have time for here, but I'll give you a quick tutorial just so you can recognize what kinds of things you might do and how to do it. So in this example, we want to create a matrix with 4 columns and 3 rows. We want parentheses on the outside, and so I'm choosing to use the P matrix environment. That's the parentheses matrix. Inside the P matrix environment, we will use the ampersand symbol to tell LaTeX when one cell is finished and when to move on to the next cell. So 1, ampersand 0, ampersand 4, ampersand -1 will tell LaTeX what should go in that very first row. And just as I said before, the double backslash is the new line character. So we use that in this environment to tell LaTeX when to move on to the second row. And so this generates the matrix that is shown on the right. There are other cases where you might use things that look like this. So in the second example, we want to create a piecewise defined function. So we have the absolute value of x equals. And now if we look at the right here, this piecewise defined function has a curly braces on the left. And then on the inside, it's like a 2x2 matrix of items. And so on the inside of the code, it will say x ampersand x is greater than or equal to 0. That gives us the first row. Double backslash moves us to the next line. -x ampersand x less than 0 will produce the second row. And you could continue on if you had more in your piecewise defined function. Another place where this will show up is if you want to align your equations so that all of the equal signs appear one right above the other. So we can see on the right-hand side what this code is generating. So in this case, we use the align star environment. And then on the inside, we're expressing it almost as if we're creating a matrix of 2 columns and 5 rows. So in this case, the first column only has the a plus b cubed term in it. The rest of them are just empty. And so that's why nothing comes before those next 4 ampersands. The same approach allows you to build tables. So there's a lot going on in this example here. Let me go through it slowly. Let's actually work from the inside out. So we want to create, let's say, a truth table like this one on the right. So we do that with the tabular environment. And if we look at that very first row, we see a vertical bar, then a C, a bar, a C, a bar, a C, and a bar. And what this is telling LaTeX is that we're going to have 3 columns. The C's say that we want to center the items in the column. And all of those bars tell LaTeX which part of the table should have the vertical bars. So in this case, we have bars separating each column and bars at the left and right ends of the table. We could replace C for center with L or R for left or right. Then on the inside, this should look pretty familiar to you now. There's this grid. The ampersands tell you when to move on to the next entry. The double backslashes tell you when to move to a new line. There's a few new things here, though. There's the \hline command. That tells LaTeX where the horizontal lines should be in the table. So if we omitted one of those, then the table would be missing one of the horizontal lines. Another comment is that this tabular environment is assuming that the items in each cell are text objects. So the T's and the F's aren't italicized, so those are not viewed as variables. That first row does require some math, and so we have to use $signs. So $A, $, produces the italics A at the top of the first column. Moving outward, we see that this is in a table environment. And so this is an example of what LaTeX calls a float. This is going to be some gigantic block in your document, and LaTeX may have a difficult time placing it anywhere. Maybe it's at the end of a page and there's not enough room to place this table. And so you can leave it up to LaTeX to find the best place for it, or you can give some instructions of what you would like. So in this example, I have square bracket, H, T, square bracket at the end of the first line. That is me telling LaTeX, try to put it here. If you can't put it here, put it at the top of the next page. And there's various other arguments you could put inside of these square brackets. The next line says that you'd like the table centered. Then we have the table itself. You can add a caption, which we did. Notice that this generates the word table and it numbers the table, and the caption appears here. Again, you can put text in there or you can put math in there if you'd like to. And we already talked about labels. You can throw a label in here so that later you can refer to the table by number just by referring to the label. One important factor here is that the label has to come after the caption. Another type of float is the figure. So this is the figure environment. Again, just like the previous one, I'm telling LaTeX, try to put it here. If you can't put it here, put it at the top of the next page. I'm also asking that it be centered. I've added a caption and I've added a label. This line here is where we are inserting the figure itself, the graphic itself. And so there's a few things going on here. In the curly braces is the name of the file. The file itself has to be in the exact same folder as the LaTeX file that you're working on. If you would like to put it in another folder, you can, but you have to specify what the path is so that LaTeX knows how to find it. And so you'd put that in with the name of the file. You can also put some added arguments beforehand. So I have width equals 4 inches. This is just telling LaTeX how big or small you want the graphic to be in the final document. I mentioned that we were using the GraphicX package. One of the nice things about using that is it gives you quite a bit of freedom to use a variety of image types. So common examples would be JPEGs, PNGs, PDF figures, TIFF figures. So that would be one of the things you would get from using the GraphicX package. One other nice feature of LaTeX is that it allows you to build your own bibliographies. In this example, at the end of my the body of my document, I have begin the bibliography and end the bibliography. And there's that number 99 in there. That's sort of a dummy placeholder number. Whatever value that is, it just has to be larger than the number of items in your bibliography. Then inside the bibliography, you have a line that begins with bib item and then some unique marker name. So in this case, I'm referencing a book that I wrote that came out in 2019. And so I called this item Richardson 19. Okay, and this will allow me to refer to this bibliographic item by that unique marker. After that, I have the bibliography written out in whatever style I chose. And so when I typeset this, it's going to appear down at the bottom, and it's going to have a unique label associated with this. In this case, it's square bracket 1 square bracket. Then in the body of your document, if you want to refer to that item, you can cite it with the \cite command. So \cite Richardson 19 is going to create a square bracket 1 in the document. If it's a book and you want to refer to a page, you can modify this so that it cites the item from the bibliography and the page number. I did want to add that there is a bibliography reference management tool called BibTeX, which plays very nicely with LaTeX. And especially if you have a long document, you might want to investigate BibTeX. It will generate bibliographies for you based on what you have cited in your document. It takes some time to learn, but once you do, it's a big time saver. And so you might want to check that out. So once you've created one of these documents, you're going to have to compile it. And I'm not going to say too much about this. It will depend on where you are using your document. For example, if you are feeling old school, you might want to compile this using the command line. But more realistically, these days, you'll probably be using a desktop app or a website, and those apps will either compile things automatically for you, or you'll have a compile button that you'll press. And so this is probably pretty easy. One thing to keep in mind is that when you compile this, all of your documents have to be in the same folder. So that is the original LaTeX file, any figures, any supplementary files you might have, things like BibTeX files, if you decide to go that route. They all have to be in one folder. If you place them in subfolders, that's fine, as long as you give the appropriate paths when you are writing your main document. So hopefully everything will work beautifully, and it'll compile and it'll spit out a beautiful PDF. But probably there will be some errors from time to time. The LaTeX compiler will spit out a log file, and it's usually a hugely long document, but it will tell you what the error is or what it thinks the error is, and you can use that to help debug your original file. Many programs also will try to present you what the error is in more understandable text, depending on what program you're using. Some errors won't completely crash your document. They're still worth fixing, but they might not be so bad that things won't compile. But it's probably good practice to fix as many of the errors as possible. Some of them could be bad enough that it just won't be able to compile and give you a document at the end. So that is the end of my introduction. You might ask, where do I go from here? Well, obviously, first thing to do would be to try creating your own LaTeX document. I do have a few resources that I'll recommend. One is this quick guide to LaTeX page that I made. It is a 2-page document, front and back, that you could print out. It has a lot of the things that we talked about here. It has the code for a bunch of the mathematical symbols and some other resources that might be useful. You can find a link to that in the description below. Also in the description is a link to a sample document that you can download and play with. So rather than starting from scratch, you may want to try playing with the document that I created. It has many of the examples that I shared in this presentation. Once you become more expert, you might want to look at what other packages are available. It's almost limitless, the number of things that you can do with LaTeX. And so you can create some beautiful, crazy mathematical expressions, interesting documents, and so forth. There is also something called TixZ, which is a language that you can use for generating vector graphics. So these are ways to use LaTeX to generate graphics within the document, so you might want to check that out if you're interested. You can make articles, reports, books, and so forth. Some other things that you can do are to create slideshows that you can use for giving presentations. And you can also create research posters using LaTeX as well. So there are many things that are available. So with that, enjoy LaTeX, and I look forward to reading your documents.